Welcome students to video class 20. In this video we are on to module 3. Okay, and the module 3 is all about the stability analysis of a control system, and to be more precise, it talks more about absolute stability. Okay, now that's in module 3. Now let's see what is, before going into these stability analysis, now what does this stability analysis means? We just want to see whether the system is a stable system or not, and what if it can do a system is an unstable system, and all of things will be dealt under the stability analysis of a system. Now before going into that, you should have an idea about the stability. Okay, now I'm going to write a statement for a stable system. The necessary and the sufficient condition is all the closed loop poles should reside on the left half of the S-plane. Okay, this we have already studied in video class in the previous videos, that is in video classes 12 and 13. Okay, you may just go through that. So in video class 12 we have seen the influences of closed loop poles on the transient response. So we have found out about 6 cases where you have dealt with the simple pole at the origin. We found out the output to remains a constant, the response remains a constant. So now this is a simple pole on the negative real axis. We have seen it is an exponentially decaying signal. So as far as a control system is concerned, this is desirable, right? So in terms of error, if you say that the error signal has to be always 0, changes at the output should remain as 0, right? So this reduces to 0, while in this case this remains as such. While in the case 3, when the simple pole is on the positive real axis, what's the meaning of positive real axis? So this is your S-plane, this is the positive real axis, that is on the right half. So whenever a simple pole on the right half, this is right half, this is left half, right? So whenever it is on the right half, what happens? This output increases, keeps on increasing, meaning the change at the output increases. So that's not good. That's going to be an unstable system. So among these 3, you will say that this is a stable system, while the other 2 are what? Other 2 are unstable. And since it is not increasing, we will call this by a term called as marginally stable system. Now as we can see here, in comparison to this case 1 and case 2, look at this. It is perfectly a stable system, right? Now as this approaches to the imaginary axis, this is getting more and more close to its unstable state, right? Now as this crosses this imaginary axis and reaches the right half, it becomes an unstable system. So what do you infer from this? The real term, as it goes into the more negative side, the system becomes more and more stable, or as it becomes more and more to the positive side, then the system becomes an unstable state. Now coming to the case 4, you have considered, instead of simple poles, you considered conjugate poles. The same is this. The conjugate poles, if it is residing on the j omega axis, something like this, right, then the output is having a constant oscillation. It will be oscillating. So you can consider that as a marginally unstable system. While in case 5, we have seen conjugate poles on the left half, right? Now when you consider that, we can see that there is a damping, maximum overshoot, and it gets damped after some time. So that means this is a stable system. That's not going to increase. While in this case, where we have seen the conjugate poles on the right half of the S-plane, so this oscillation is increasing as t increases. So this is an unstable case. This is a stable system. The other one which we have seen, this is marginally stable because the oscillation is neither increasing or decreasing, so you can consider that as a marginally stable system. Now, look at this. As you compare this, the conjugate poles, as it becomes more and more closer to this, the oscillation increases. That means, say, instead of these poles, suppose these poles resides over here, then you will be having more oscillations here, but at the same time that will get damped. So till it reaches this point, these 2 points, this will be having an oscillation, but it will be damping. So the damping requirement is more as this pulse approaches to this imaginary axis, and once it crosses this imaginary axis, what will happen? This will be happening. So the oscillation is not at all under control. That will be an ever increasing oscillation. So proving that, so you can come to that in view of this, we have made a statement something like this, okay, that is, for a stable system, this is very important. For a stable system, all the closed loop poles should reside on the left half of the S plane. I'm again repeating by showing an example. All the poles, so okay, all the poles should reside on the left half of the S plane for the system to be stable. So this is a stable system, while this is an example. Even if, say, you have say suppose you have 5 poles for this system, and all the 4 poles reside on the right half, only 1 pole on the right half, okay, all the poles on left half and 1 is right, and this is enough for the system to be unstable, okay, right? Okay, now let's see, when you come into the stability, you can have 2 different types of stability. One is called as the absolute stability, the other one is the relative stability. Okay, absolute stability and relative stability. So I'll just explain what is this absolute stability. Now, absolute stability, it gives you just an yes or no answer, to a question whether the system is stable or not. Okay, so whether the system is stable, it will be giving you a answer yes or no. That means you can just know whether a system is stable or not. So this is more of a quantitative analysis of a stability. This absolute stability can be considered as a quantitative analysis because it just gives you an information whether the system is stable or not. Okay, right? While the relative stability, it not only gives you an yes or no statement to this question whether the system is stable. Okay, is the system stable? It gives you a measure. It gives you the measure of the closeness of a stable system to instability. Okay, right? So that means as I've mentioned here, so it will give you more information of the system, whether the system can how far it is closer to an unstable state. Okay, and there are different parameters which dictates that, and some of those which we have studied in time domain analysis as maximum overshoot, okay, then damping ratio, and these are called as a time domain specifications, and some are yet to learn, like gain margin and phase margin. These are called as a frequency domain specifications. Now, by using all these parameters, you can compare the stability of a system with its how much it is closer to an unstable instability. So even by using this relative stability, you can think of having measures to make an unstable system to a stable system if you have a relative stability. So relative stability is a more of a qualitative analysis. It is a qualitative stability analysis. So hope you understood these two types of stability. Stability one is absolute stability. It will just give you an answer whether the system is stable or not. That is either yes or no. So that's a quantitative analysis. While relative stability, it will be giving you an idea whether the system is stable. Not only that, it will be giving more insight that whether that system is, whether it is far away from instability or it's close to instability, or even when a system is unstable, can you make that system, or in some way or other can we make that system to a stable system. Also relative stability, by doing relative stability analysis you will get a more information than the absolute stability. Okay, so now coming to absolute stability. Okay, now absolute stability. And absolute stability is a topic which is more concentrated in this. We'll be concentrating more on this absolute stability in this module. Now, as I just told you, absolute stability is a quantitative analysis and it will give you just an answer whether yes or no to the question, is the system a stable system? Okay, you will be just getting a simple information whether the system is stable or not. Okay, now for finding out the absolute stability, it is required to find out the closed loop poles. Okay, now how will you get the closed loop poles? We know that the closed loop transfer function is given by gs by 1 plus gs hs, right? So how will you get the poles? You can equate this thing to 0, right? And what is this called? This 1 plus gshs equal to 0 is what is called as the characteristic equation of the closed loop system, right? So this is called as the characteristic equation of the closed loop system, right? So upon solving this, you will get, say, some roots called as, since it is poles, okay, closed loop poles, let's denote that by p1, p2, p3, etc. Okay, suppose it is an nth order polynomial. This is a polynomial, and if it is an nth order polynomial, you can expect n poles, right? And how will you check whether it is on the right half? Now what we need to understand is we need to find out whether the roots lie on the right half or the left half, right? Now this is an S-plane. S-plane means this is sigma and j omega. Now which actually determines whether the pole is on the right half or the left half? It is determined by the sigma value or the real value of that S, right? So suppose, say, I'll just give you an example. Say in the example, say consider this example, you have 4 poles. One is at -2, the other one is minus 1 minus 3j. Obviously the other will be 1 plus 3j, and the other is at 3. So you can say this is -1, sorry, this is -1. So you have a pole at -2, you have a pole at -1 with minus 3j and plus 3j, because complex conjugates occur at base. So you have 3 poles, right? One at -2, -1 plus minus 3j, -1 plus 3 minus 3j, and you have one more pole residing at 3. So look at this. So what actually determines whether it is on the right or the left half is the real value. So look at this, real value. Here also it's the real value. Here also you have this real value. Here also you have the real value. So the real value, if it is negative, you can say that that's in the left half, and if it is on the right half, it is a. So what can you say about this? If suppose in a question you have found out the pole something like this, and if you are getting an answer, you can straight away say the answer is it is an unstable system. Okay, so such analysis we call as an absolute stability, and it won't be giving you an idea whether you can make it a stable system or not, or it won't dictate any other parameters, okay, as we have studied earlier. So it will just give you an idea give you an information whether the system is stable or not. So in this case, the system is an unstable system. Now, by solving, so you just need to solve to get the root location. Okay. Now, there is a problem with while solving. Say, look at this. Now, this polynomial, say, call this as q of s. This polynomial 1 plus gshs is q of s is equal to 1 plus gshs. So, when this q of s is having a power higher than 3 or 4, it is, say, for example, if you have a q of s something like this, s raised to 10 plus s raised to 9 plus s raised to 8 and so on, right? Plus, say, some 2 is equal to 0. So this is actually a higher order characteristic equation. Now, if you want to analyze such a system, whether the system is a stable system or unstable system, it's very difficult to solve this. Okay. And one more point to be noted is, we are not concerned about the exact location of the pole. We just want to know whether the system lies on the left side or on the right side. Okay, that is, it is not necessary. So this is another statement. It is not necessary to find the actual location of the closed loop holes. Okay, closed loop holes. So this is a statement which actually gets developed into a method by which we can see whether the poles of the characteristic equation reside on the right or left without solving by our conventional methods. Now, utilizing the conventional method, it is good for up to power 3. You can solve a quadratic equation. You can also solve a equation with the power 3. Now, if it becomes higher powers like 10, s raised to 10 and so on, it's very difficult to have the conventional method of solving and find out whether the system is stable or not. So it's not necessary to find the actual location, and if it is not necessary, you don't need to always resort to solving an equation. There must be some other method, and that method is what is called as Routh-Hurwitz criterion. Routh-Hurwitz criterion, and this is the main Routh-Hurwitz criterion. Okay, and this is the major topic of this module 3. Okay, now how to do this Routh-Hurwitz criterion. Now you have so for this, say, I'm considering a polynomial. Consider an nth order characteristic equation. Okay, so let the characteristic equation be q of s. Now, if it is an nth order polynomial, say, I'm assuming this to be s raised to n plus a1 s raised to n minus 1 plus a2 s raised to n minus 2 plus a3 s raised to n minus 3, and it goes on like that up to an s raised to 0. So the first thing is that before going into this Routh-Hurwitz criterion, you have a preliminary test. Okay, you have a preliminary test. Okay, now preliminary test doesn't mean that you don't have to do this Routh-Hurwitz criterion. You need to do, but before going to this, you need to have do a preliminary test on this q of s. That is, for the roots to lie on the left half. Okay, for the roots to, this is what's our main objective of solving this. We want to find out whether all the roots is on the left half of the s-plane, right? Now, there is a condition for the roots to lie on the left half, right? Number one is no missing term in the polynomial. in the polynomial, right? In the polynomial. That is the condition 1. So just look at this. What's the meaning of this? Missing term means, say you have s raised to n, then you have s raised to n minus 1. Suppose imagine that after this you have s raised to n minus 3, don't have an s raised to n minus 2, then there is always a chance for the system to have one of the poles, at least one of the poles on the right half of the s-plane, and that gives the system an unstable system. Okay, so another point is all the coefficient of each term must be positive. Okay, so what is this preliminary test for? This is for left half poles. For the left half poles, first of all you must have a thorough testing on it, and you can just write down before applying this Routh-Hurwitz criterion, that is, yeah, there can't be any missing terms in between, and coefficient of each must be positive. And one more point to be noted is, now even if it passes this test, coefficient of each must be positive and no missing terms in the polynomial is actually the condition for the polynomial to have all the left half poles. This doesn't mean that by achieving this condition the poles should not be in the right half. It can be chances for the poles to reside in the right half. Now for any left half poles you are going to have this character. Okay, so this is just a preliminary test. You need to do this Routh-Hurwitz criterion for finding out the exact answer. So this won't be giving you an exact answer to the question whether the system is stable, but you can have an assessment before doing this Routh-Hurwitz criterion. For anyway, for a left half poles, for the system to be stable or for all the poles to reside on left half, 2 points are to be important. One is there should not be any missing terms in between the polynomials. Another is all the coefficients, that is 1, a1, a2, a3 up to an are to be positive. Okay, now after having this preliminary test on the given polynomial or the characteristic equation, you can proceed to Routh-Hurwitz, or in short I will be calling it as RH criterion. Okay, now let me explain what is this character RH criterion. For this RH criterion, again I am considering this Q of S to be the general equation, that is s raised to n plus a1 into s raised to n minus 1 plus a2 into s raised to n minus 2 plus a3 into s raised to n minus 3, etc. up to an. Okay, now what must be the step 1? So the step 1 is to develop a Routh array. Okay, so I will explain what it is. You don't have to worry about this. What is this Routh array? Maybe it's a new term for you. Okay, so array is nothing but, you can think of array as what? Array as a combination of some rows and columns. So this is an array, right? Rows and columns. You have some rows and you have some C1, C2, C3 and so on. Okay, R1, R2, R3 and so on. So these are R1, R2, R3, etc. C1, you can have this much columns as C1, C2, C3 and so on, right? So this is an array. Now what is this Routh array? Now to develop this Routh array, this is the procedure. You may write write like this: s raised to n, s raised to n minus 1 in the descending order of the powers of s raised to n minus 2, s raised to n minus 3, and it goes on up to s raised to 0. Okay, so this array is having a column. How many columns it will be having for an nth order polynomial? So you will be having an n rows, right? You will be having n rows because it's an nth order polynomial, right? Okay, so this is an nth order polynomial. And now coming to the columns. Now what you need to, how to form the column? The column is formed by writing the corresponding coefficients of this. So how to write coefficient? You need to write the coefficient on the first column. You need to write the coefficient of, coefficient of n. In the second column you need to write the coefficient of n minus 2. In the third column you need to find out, put the coefficient of n minus 4, n minus 6, and it goes on, right? It's never ending till, it depends on how much terms it has. So there is no limit for this. Once this n is fixed, the rows is fixed. So this can have n is equal to n, n minus 2, n minus 4, n minus 6, and so on. So you have the columns. Now these are the columns. So there are rows corresponding to each, right? Corresponding to the powers of s raised to n, s raised to n minus 1, and you need to draw like this. Then you have the column corresponding to n minus 2, n minus 4. Okay, now coming to this s raised to n. So you have so many cells, so you need to write the fill this cells. Now what to write over here? The thing that is to be written over here is the coefficient. So in the first column, this is a step for s raised to n and s raised to n minus 1. You may fill this from the given equation. You are from this given equation. So for filling s raised to n and s raised to n minus 1, you should use this, right? Okay, so what about this? The nth, s raised to n. So s raised to n's coefficient is, you need to fill that coefficient. Now what will be here? This will be the coefficient corresponding to n minus 2, which is a2, right? And what will be the coefficient corresponding to n minus 4? N minus 4 will be, n minus 4 will be what? Will be a4, right? The other one will be a6, and so on. What about in the second case? Now your n is n minus 1, s raised to n minus 1 means this n minus 1 coefficient will be a1. Okay, now if this is the nth coefficient of this term, the n minus 2th term will be a3, right? This is n minus 1, so you need to write like this: a3, then a5, a7, and so on, right? Okay, now this is it. So the first row, 2 rows are to be completed from the given equation. Okay, hope you understood. That is, you start from the highest power coefficient, then the n minus 2th terms. That's the next coefficient. Next coefficient will be the n minus 4th, n minus 6. Similarly, when you come to n minus 1th, what is n minus 1 minus 2? It will be n minus 3. So a3. N minus 1 minus 4, n minus 5, a5, a7, and so on. Okay. Now, once you have developed this, you can find out the rest of the rows from these two values. So next row that is to be filled is s raised to n minus 2, right? Now, how will you evaluate this s raised to n minus 2? Okay, so I'm just calling this as b1. Okay, I will use a different name. Calling this as b1, b2, b3, and b4. Okay, I'll just write how to find out this b1. b1 is actually equal to this is how a1 into a2. It sounds similar to determinant, right? a1 into a2 minus a1 into 1 into A3 divided by A1, right? So this is the base element for this row, right? I will explain, you will understand why I call that as a base element. Now coming to B2, B2 is nothing but, how to calculate B2? B2 is this thing, right? So how will you evaluate B2? B2 will be A1 into A4 minus 1 into A5 divided by A1. So this is your reference column. Based on this column only, we will be evaluating the rest of the elements. So how will you find out B3? B3 will be again A1 into A6. A1 into A6 minus A7 into 1. A7 into 1 divided by A1. Very, very important to remember this. Everything okay, right? So you are actually finding out the determinant by keeping the first column with the other columns. Okay, so based on that you can find out B1, B2, B3. Okay, so that's how you find out s raised to n minus 2. Now how will you find out s raised to n minus 3? That is, let us call this a C1, C2, C3 and C4. How to find out this? Now, so C1 is evaluated. When C1 is evaluated, the role of A1 will be given to B1. Okay, and then C1 is evaluated from the two rows above this. Okay, from the two rows, that is from s raised to n minus 1 and s raised to n minus 2. B1 being the base element here. Now keeping that in mind, you can say that C1 will be B1 into A3, B1 into A3 minus A1 B2. What about C2? C2 is B1 into A5, right? B1 into A5 minus B3 into A1 by B1. And what about C3? C3 will be B1 into A7. Look at this, B1 into A7, right? B1 into A7 minus A1 into B4, A1 into B4 divided by B1, okay? So similarly, you can find out now, coming to the s raised to, how will you find out s raised to n minus 4 term? So how will you fill this row? So then you need to take this as your row, as your base element, and use these two upper rows to find out this element. That will be, so I'll just tell you, okay, you may just note down. This will be C1 into B2 minus B1, C2 by C1. The next term will be C1 into B3 minus B1 into C3 by C1, and it goes on like that. Okay, so let us call this as, and you have evaluated this, and finally you have arrived at, say, some D1. Okay, all these are immaterial. Now this is the, so after finding out, and this is a kind of determinant that we have solved, and this type of determinant we call as the Hurwitz determinant. Okay, this is Hurwitz determinant, and this array is called as a Routh array. Okay, now that's why the resulting criterion that is to be applied is called as a RH criterion. Now we will say what is a criterion. So based on this, you have a RH criterion, and what does this RH criterion says is, you just check the, after developing this Routh array, just go to the first column and see if there is any sign changes as you go from top to bottom of the first column. The number of sign changes means, say for example, say suppose you have evaluated something like this, 1, 2, 4 and minus 4, 3. Say suppose you have only 4 rows in the first column and you have got these values. What is the meaning of number of sign changes? This is a positive quantity, this is a positive quantity, then it becomes a negative quantity, right? So that means there is a sign change, right? Now from a negative quantity, again it becomes a positive quantity. So in this, as you move from top to bottom of the first column, you have seen that there are two sign changes. Okay, now what does this RH criterion states? RH criterion states that the number of right half poles, and what is the role of this right half poles? This aids what? Or this aids the instability, or this causes the instability, or this makes the system unstable, the right of poles. The right of poles is equal to the number of sign changes in the first column of what? Root array. In the first column of root array. So in this example, you have number of sign changes is equal to 2. That means you can see that on the right half of the S plane, you have 2 poles, and we are not aware about the location. That's why I told you that the it is not necessary. That's why I have written the statement in the it is not necessary to find the actual location of closed loop. You don't need the actual location. If you have the RH criterion, you will be getting the number of rods without solving the root. So this will be of a very great help when the polynomial is of the highest higher orders. Okay, so the criterion states that for a system to be the number of right of poles is equal to the number of sign changes, or you will say that for a system to be stable, RH criterion states that the number of sign changes should be in the first column of what? Of roots array has to be 0, isn't it? Has to be 0. Okay, right? So in this case, the system is an unstable system because you have two sign changes. So you will understand it as we do some problems concerning this RH or applying this RH criterion. Okay. Now you have a problem. Question 1. A characteristic polynomial is given by the polynomial s raised to 4 plus 2s cubed plus 15s squared plus 18s plus 12. So what is the preliminary? Before going to RH criterion, you need to have this preliminary test. You can write. What is that? Preliminary test. No missing terms, right? No missing terms. Then all coefficients are positive. Okay, but because of this fact, you cannot say that the system is a stable system or not. Now this is just the condition. If this, you cannot, this is not a converse statement. That is, all the characteristic equation with all left half poles will have this nature. That doesn't mean that if a characteristic equation has this term, these conditions satisfied, that will be having the left half poles. Okay, the converse is not true. All the left half pole characteristic equation will have this character, but you cannot say in the reverse direction, that is, okay, all the characteristic equation which satisfies this condition should have left half pole. No, that's not possible. That is not necessary. That's not necessary. It can go wrong at times, but this you can ensure all the left half pole characteristic equation will have these characters. So that's why we simply do this preliminary test. Okay, now how to apply this this criterion. Okay, hope you understood why this term RH Ruth Hurwitz criterion, because in the first step we will be developing a Ruth array, and in order to develop the Ruth array we apply Hurwitz determinant. So this criterion is actually a combination of a Ruth array as well as the Hurwitz determinant, hence this criterion is called as a Ruth Hurwitz criterion. Okay, now let us see what it is. How to so the first step, as I've told you, to develop a Ruth array. How to develop a Ruth array? Write down the powers of S in the descending order: S cube, S square, S raised to 1, and S raised to 0. Okay, so fill the first two rows from the columns. And how will you name the columns? The columns has to be named as, say, n minus 2, n minus 4, and minus 6, and so on. Now this n refers to what? This n refers to the first power of that. Okay, so that particular row. So when you consider the row, that the power of that row is what should be considered as n. So in this case your n is 4. So what is the coefficient of this 4? So s raised to 4 is 1. Then what is n minus 2? If n is equal to 4, n minus 2 is 2, s square. And what is a coefficient? That is 15. Right, what about n minus 4? When you do again a 2, n minus 2, n minus 4, that is 4 minus 4, 0. So this is 12, right? 12, and the rest is 0. Now wholly fill the S3. Now when you come to the second, this row, your n becomes 3. Now what is this coefficient of n? N is 2, right? What is the next term? Next term will be 18. N minus 2th term will be 18. And what will be n minus 4? There is no s raised to minus 1. So all the rest are going to be 0. Now remember, do remember that the first two rows are filled from the given characteristic equation. Okay, hope you got that right. Now how to find out this s square? S square, you must treat this as your base column and this is your base element. Using this element or using this column, you can evaluate the row element of S2, S square, right? Now what is the first term? First term will be 2 into 15. This is 2 into 15 minus 18 into 1 divided by 2, okay, which is 30 minus 18 divided by 2, or it is equal to 12 by 2, which is equal to 6. So the first term will be 6 of S2, right? S square. Now what will be the next term? Next term will be 2 into 12 minus 1 into 0. So 2 into 12, that is 24 by 2, which is 12. So how will you find out s raised to s square? The next term will be 2 into 12 divided by 6, which is equal to 24, which is equal to 12, right? So you can find out in this way. So the next term will be 6 into, next is 2 into 0 minus 1 minus 0. So the rest is going to be 0, right? Now how will you evaluate s raised to 1? Now evaluating s raised to 1 is, you need to take this as your base element, and the upper two rows are to be used for finding out this. So this will be, so when you consider this s1, the first element of s1 will be what? 6 into 18 minus 12 into 2 divided by the 6. Okay, so this s raised to 1, you can find out the answer to be 14. So this will be 14 and the rest is 0, right? Okay, say next is 6 into 0 minus 2. Okay, so all this becomes 0. Now what about the s raised to 0? Now when you come to s raised to 0, you need to use the upper two rows. That is, you can use this base, this as the base, 14 into 12 minus 6 divided by 14. So the answer is going to be 12. Okay, right? So once this is actually, this formed, the array is what is called as the Ruth array. This is what is called as a Ruth array by using, and how the Ruth elements are found out. So found out by Hurwitz determinant. Now, what is the criterion? How to next is RH criterion is to be applied on the first column. Okay, now applying the first column, consider the column, find out the number of sign changes. All the elements are positive in nature, right? So there is no sign changes between the successive elements, right, of the first column. No sign changes between the elements. So that means the number of sign changes of the consecutive elements of the first column is equal to 0, and that is the condition for the system to be stable, right? And that is number of RH poles, right half poles, is equal to 0. So there is no pole to make the system unstable, therefore the system is a stable system. Okay, system is a stable system. So question number 2, you may take down this question. A characteristic equation is given by P of s is equal to s raised to 4 plus 5s cube plus 5s square plus 10s plus 12. Check whether the system is the stable system by applying Hurwitz criterion. Okay, so you may just proceed just as we have proceeded in this question, and you may do it by yourself, and we'll be discussing the answer during the discussion time, okay, today itself. Okay.